the last two lectures, we have been discussing reciprocal lattice and its application to computations in crystallography. This lecture, one will look at how reciprocal lattice and diffraction can be related to each other. But just before that, let us take a few examples of a real lattice and a reciprocal lattice drawn together to show the relationship between the real space lattice and the reciprocal lattice relationship. So, let us begin with, let us say, an orthorhombic lattice, a primitive orthorhombic lattice. So, in real space, so I have only lattice points at the corners. So, I am drawing a projection of the reciprocal lattice along the C axis. So, this is my A axis, B vector, and the C vector is perpendicular to the figure. Now, and let us also put some numbers to it. Let us say A is equal to 2 angstroms, B is equal to 4 angstroms, and C equals 8 angstroms. These are arbitrary numbers that I have put. Now, correspondingly, I want to sketch out the reciprocal lattice. So, the reciprocal lattice would have basically A star, B star, and C star. And since this is an orthorhombic, which means all the 3 axes are at 90 degrees to each other, which means alpha equals beta equals gamma is equal to 90 degrees. It also implies that in the reciprocal lattice space, alpha star equals beta star equals gamma star equals 90 degrees. Now, sketching out the reciprocal lattice, so what should be A star first? So, A star, in this case, since it is all 90 degrees, it would be 1 upon A, and that would give me 0.5 angstroms. Now, B star would be 1 upon B, and B is 4, so that would give me 0.25 angstroms, and C star, which is going to be 1 upon C, and that is going to be 0.125 angstroms. Anyway, we are only drawing the projection along C. So, the reciprocal lattice would look something like this. Where this is the vector A star, this is the vector B star, and C star is perpendicular to the figure. So, you can see that the shape remains the same, but the dimensions are different, and I made a small mistake. This is not angstroms here, this is reciprocal. So, this is angstrom inverse. Now, let us say that I have plane, let us say in real lattice space, I have these set of planes. Now, this is a plane which has Miller indices 1, 1, 0. Now, in the reciprocal lattice, where is this set of planes being represented? So, if I start labeling each of the lattice points, so let me also label the lattice point. So, in the real lattice I have labeled, let me also label it out here. These are the reciprocal lattice points. So, this would be, for example, 0 1 0, 0 2 0, 1 1 0, 1 2 0, this is 1 0 0, this one is 2 0 0, this is 2 1 0, 2 2 0. This is a reciprocal lattice vector R star, and this particular reciprocal lattice vector R star 1 1 0 is essentially nothing but 1 times A star plus 1 times B star plus 0 times C star. Now, this point, this reciprocal lattice point 1 1 0 represents the set of planes which are the 1 1 0 planes in the real lattice. R star vector is perpendicular to the 1 1 0 plane, and the magnitude of the R star vector is reciprocal of the interplanar spacing of the 1 1 0 plane. So, R star 1 1 0 magnitude of this is equal to 1 upon D 1 1 0. So, in a way what we have done is we have represented a set of HKL planes as a point in the reciprocal lattice, and that way every point in the reciprocal lattice represents a set of HKL planes. Suppose I was looking at a cubic lattice, a primitive cubic. So, I have again lattice points at the corners, and this is my vector A, my vector B, and this is a projection along the C axis. And let us say my A equals B equals C is equal to 2 angstroms. Let me draw the, and incidentally I should say that this is, if this is my origin in this reciprocal in the real space lattice, this is the origin here. So, one can superimpose these two lattices and then look at the relationships as well. I did not superimpose, but because the diagram becomes confusing. So, out here this is my origin. Now, let me draw the reciprocal lattice as well. So, now what is the magnitude of the reciprocal lattice vectors A star, B star, C star? They will all be equal, and they would be essentially 1 upon A, and that gives me 0.5 angstrom inverse. And of course, the angles between A star, B star, C star are alpha star, beta star, gamma star, they will all be equal to 90 degrees. So, these are my reciprocal lattice points. this is the vector A star, this is the vector B star, and C star is perpendicular to the figure. Now, consider for example, a plane 1 1 0. In the reciprocal lattice, the set of planes 1 1 0 will be represented by the reciprocal lattice vector R star 1 1 0. This lattice point out here represents essentially the set of parallel 1 1 0 plane in the real lattice. So, one can also label each lattice point with their coordinates. So, this would be 0, 1 0, 0, 2 0, 0, 3 0, 0, 4 0. Similarly, this would be 1 0 0, 2 0 0, 3 0 0, 4 0 0, and one can say this is 2 1 0, 2 2 0, 2 3 0, and 2 4 0, and so on. One can label all of these. Consider another set of planes. Let us say 1 2 0, and this was 1 1 0. So, 1 2 0 will be represented by this particular reciprocal lattice point, and the vector representing these set of planes would be R star 1 2 0, and so on. So, and these vectors R star of course will be perpendicular to those individual planes. So, what I can write then, that each lattice point h comma k comma l, these coordinates, in reciprocal lattice space represents a set of parallel planes HKL in real lattice space. And the reciprocal lattice vector R star HKL encoded in it is the normal direction to plane HKL, and its magnitude is reciprocal to the interplanar spacing D. So, reciprocal lattice is giving us a lot of information in a very simple diagram as a set of points. We will take one more example, a third example in which all the axes need not be orthogonal. Let us take a primitive hexagonal lattice. So, again lattice points at all corners. This is my vector A, this is vector B, the vector C is again perpendicular to the figure, and this angle is gamma. So, in this case, let us say A equals B equals 2 angstroms. Let me put C as 4 angstroms. Alpha equals beta. So, remember angle alpha is the angle between the B vector and the C vector. Angle beta is the angle between the A vector and the C vector, and both of these angles are 90 degrees, and gamma equals 120 degrees. Now, let us try to sketch out the reciprocal lattice for this. Let us first write down how are my A star, B star, C star related. So, the vector A star perpendicular to the B vector and the C vector, B star perpendicular to vector A and vector C, C star perpendicular to vector A and vector B. Now, let this be, let us say, the direction of the B vector. Now, A star vector, this is the direction of the B star vector that I have drawn. Now, the A star vector must be perpendicular to the B vector. Therefore, if my B vector in the real lattice is horizontal, then my A star vector should turn out to be perpendicular. So, it will be vertically down, and then let me complete the diagram after this. So, here I have, this is my vector A star, this is the vector B star. So, A star perpendicular to B and C, it works out well, because C star will be again be perpendicular to this figure. This angle out here is gamma star. Now, what about the angles between the vectors A star, B star, C star? We also need to figure that out. So, alpha star equals beta star equals 90 degrees. This is because alpha and beta in the real lattice are also 90 degrees. However, gamma in the real lattice is 120 degrees. So, what should be gamma star? So, we can easily compute by using the relation that we derived in the previous lecture, which is cos alpha cos beta minus cos gamma divided by sin alpha sin beta. If I plug in the values now, so I will have basically minus cos of gamma upon sin alpha beta are 90 degrees. So, therefore, this value is simply minus cos gamma. Now, gamma is 120 degrees. So, minus cos of 120, well, cos of 120 is minus half, and there is a negative sign outside cos. So, therefore, this will become plus half. This implies that gamma star is simply 60 degrees. And then one can also compute what would be A star, B star, so on, by simply looking at that what is A star. One can actually calculate from first principles that the magnitude for, or the vector A star, which is simply B cross C divided by the volume, and its magnitude would simply be the magnitude of the cross product divided by the volume. And we also know that the volume is simply given as, I can C dot A cross B. And if I do all this calculation, what I will get would be that A star, the magnitude for A star would be 1 upon root 3, and this will be the same as the magnitude for B star. C star, which is actually perpendicular to the AB plane, would be simply be one upon the interplanar spacing of the 0, 0, 1 plane. This then can be written as what is the interplanar spacing of the 0, 0, 1 plane? It is nothing but 4 angstroms, so which is basically the value of C axis. So, 1 upon 4, and that is 0.25 angstrom inverse, and here also this is the units are angstrom inverse. Okay, with this I finished the discussion on this, and now I want to relate the diffraction with the reciprocal lattice, how this can be related. This will be continued in the next lecture.